Hey everyone, thanks for the invite. Sorry we're a little bit late, we're still on West Coast time. Flew in from San Francisco last night. So thank you for giving us the opportunity to speak here. I'm from Rigetti Computing, I'm a software engineer there, and I would love to talk to you about some of the software that runs the quantum computers that we build down in Berkeley, California. So Rigetti Computing is a full stack quantum computing company. And when I say full stack, I really mean it. We build both the hardware, the devices, and the software necessary to do quantum computing with superconducting qubits. So here's some pictures of our lab down in Berkeley. And this is currently where we have a fleet of quantum computers, some of which are publicly accessible over the cloud. And this here is a picture of our fabrication facility in Fremont, California, and that's kind of where everything begins. So we built this facility from scratch, specializing it for the manufacture of quantum integrated circuits, and we think this is likely the first facility of its kind that's dedicated to making superconducting quantum processors. And so that's what one of the quantum devices that we manufacture looks like. This is an 8-qubit device, but obviously we're scaling up, and this type of device for people who are familiar with more traditional computing, it looks a little bit foreign, but there's actually a number of things that are familiar about it when you compare it to sort of traditional semiconductor manufacturing. It's printed on a piece of silicon, a silicon wafer, and then we spray on metal using various kind of traditional fabrication processes. The big difference, obviously, is with semiconductors is that this is not semiconducting, but rather it becomes superconducting when we sufficiently cool it down. But I'm not here to talk about the fabrication process, because I don't know a ton about it. I'm here to talk about the software, which I do know a lot about. And in particular, I want to give you kind of a behind-the-scenes look at the software that it takes to actually run one of these devices and get it accessible for people like you to run programs. So my personal background is in software engineering. My last job was working at LinkedIn. So if you received many messages, recruiter messages, I'm sorry about that. So I spent 3 years there and then wanted to try something completely different. And Rigetti Computing has a very diverse staff in terms of background. We have software engineers, physicists, theorists, mechanical engineers, really anyone needed to come together and build this very difficult machine. So, I'd love to kind of give you a bit of a behind-the-scenes look in the software that it takes to get your program down to our computers. So the way we write quantum programs at Rigetti is using a language that we specified called QUIL, and that's short for Quantum Instruction Language. Now, QUIL looks very similar to assembly code. It's a step-by-step list of operations that should be executed on particular qubits. So on the left, you can see some of the examples, and you'll probably be familiar with some of these gates, but on the right is how you would execute them with QUIL. You specify the gate name and then the qubits that gate operates on. So for instance, there's an Hadamard, C0 gates, and so forth. And then to finish off your program, you append measure instructions at the end. And that reads out a single bit of information from the qubit and stores it in a classical register for you to then continue doing any more work with it. So step one of executing a quantum program is obviously get it into this format and describe to us the gates that you'd like to perform. So the QUIL program is packaged up and sent to us over the cloud. And because every quantum computer is, or beside every quantum computer is a regular old classical computer that we call the control computer, and it has a number of steps to do with that quantum program before it can actually be physically realized on our devices. So the first step is compilation. And to explain what a quantum compiler does, I'll first contrast it with a compiler for a classical computer. So if you take a language like Scala, which is my favorite programming language, and you compile it, it eventually gets compiled down to JVM bytecode. So another way to say that is that the source language is Scala, the target language is the JVM bytecode, and then the compiler itself is written in Scala. For us, we made some unique choices for our compiler. So we take in Quil as input, and what we output is a subset of Quil called ProtoQuil. So our devices do not support arbitrary unitary operations. They only support a few different types of gates that we've calibrated. So to take an arbitrary program that you give us and get it to something that can actually run on our hardware, we need to perform various identities and so forth to transform your program from which is arbitrary gates into a program that our computers could understand. So that's what our compiler does. And ProtoQuil is the result of that, which is Quil that is restricted to a subset of operations that can be performed on our computers. So our compiler is written in Common Lisp, which for people who have been in software engineering for a while shouldn't be a surprise. It's a good language for doing any sort of structural matching and transformations and so forth. So even in amongst the computers that we have at Rigetti, there are different natural gate sets. And so the compiler needs to be customized for each one of these to allow it to get down to the most efficient, most optimal ProtoQuil program for the Quil program that you give as input. So for instance, what the compiler does is there's a number of, it can take several lines of instructions and also optimize it into one. So there are a number of identities, programs on the left, which are longer than equivalent programs on the right. And our compiler is aware of some of these transformations and can make them for you to get the program down to a more optimal size. So this is obviously really an exercise in linear algebra. Each of these is a matrix operation, which then can be decomposed, change the basis, all sorts of things to get us to the type of code that we want to run on our computer. So another challenge that the compiler has to deal with is the limited subset of, or the limited connectivity of our devices. So the qubits on our devices are not all-to-all connected. Rather, you can only perform 2-qubit operations on neighboring qubits. So to perform an arbitrary quantum program, you need to take any 2-qubit gates on non-nearest neighbors and get them into a program that only performs on nearest neighbor qubits. So here's a picture of our 20-qubit device. If you zoom in, you can see that each qubit is connected to at most 2 of its neighbors, or 3 of its neighbors rather, and some of the qubits obviously around the edges even have fewer neighbors than this. So there's one kind of orphan on the bottom left that's only connected to one other qubit. And so how does the compiler deal with this? Here's the same picture again, but in graph form. It shows you the various edges that we have active and the qubits. So if we wanted to, say, perform an operation against qubits 1 and 10, we would first have to perform a series of swaps to get the quantum information next to each other in order to perform those operations. And so the compiler is both kind of doing this linear algebra problem, which is taking arbitrary quantum programs and turning them into our natural gate set. And it's also doing this sort of graph optimization problem, which is to try and figure out the minimum number of extra operations it needs to throw in there in order to take a fully connected program and turn it into something that runs on our limited connectivity devices. All right, so that's step 1. And the next step is to convert these abstract instructions that come out as a result of the compiler into something that's physical. So our quantum computers respond to bundles of photons that are sent to them by pulse generators. And the pulse program is a series of these pulses. So if you extend my compiler analogy from before, there are usually multiple steps in compilation. So for instance, with Scala, you compile it down to JVM bytecode, and then that JVM bytecode again gets converted or translated into native machine instructions that the CPU would understand. And similarly with our quantum programs, the final step is to take the Quil code and turn it into a pulse program, which is something that the computer will actually react to. And we do this using Python. So I'm going to explain a little bit more about what I mean by pulse programs. Let's say the qubit is in the 0 state. to flip it to the one state, we need to send it an RxPy instruction, but that instruction on its own has no meaning to the quantum computer. So the pulse is the thing that will actually cause it to perform some sort of quantum mechanical interaction. So when we send the pulse to the qubit, it responds by flipping the state. I put a lot of work into that animation, so I hope you're impressed. Let's see it one more time. Oh, cool. All right. So it works. Take a moment to think about how this differs from a classical computer. So in a classical computer, you have a CPU, and on it, it has various accumulators and circuits and so forth for doing different types of computations. You then send the data through the CPU. So this is really complete opposite of a quantum computer, where in a quantum computer, the data is what you send in. Or the data is what stays, rather, and then you send in the program. So as opposed to the data kind of flowing around the computer, you're actually keeping the data in one place and then sending in the program. By varying the length of the pulse, you can change, for instance, how far the state of the qubit moves. With a short pulse, it may only go a quarter of the way around, and with a longer pulse, you can get it to do a full RxPy instruction. So you can kind of think of the pulse program almost as like a musical score. You need to know which pulses to play, which notes to play, in which order, for how long, and how loud, and at what frequency, and all these sorts of things. So this gets us kind of to the real crux of the difficulty of my job and the difficulty of building software that runs these quantum computers, and that is that they're analog by nature. So each of these pulse parameters can be varied in a number of different ways, and they're all analog parameters. So we're trying to take something that's digital, like an X instruction, and turn it into something that has a number of real numbers involved. And it's a real challenge for us on the software engineering side to actually find these numbers. Every parameter is a continuous real number, and performing highly accurate numerical calculations to find these things is obviously incredibly important. And then if that weren't already hard enough, the other challenge for the software is that these parameters are not fixed. So various changes to the computer's environment, including even the temperature of the air outside, will create noise and affect its operation. So programs that you run in the morning will look significantly different than programs that you run in the evening. So this means that a system has to continuously be undergoing recalibration in order to find and correct the right parameters depending on the environment. So there is an enormous amount of data being collected every day about these quantum variables and their effect on the computer's accuracy. And, you know, this is kind of the data mining, big, interesting problem that a lot of software engineers are really excited about at other companies. But, you know, back when I was at LinkedIn, I was mining information about people and your relationships and whether you'd respond to my job invites. But now we're mining and trying to take in all this data that's coming out of our instruments and trying to match it against the changes in the environment in order to keep the computer calibrated. All right, so assuming you've managed to get all that right and you've kept all these parameters calibrated as changes to the environment happen, you can then send it to the quantum computer to execute. So our quantum devices, like the one I showed in the picture earlier, only become superconducting at incredibly low temperatures, just above absolute zero. So therefore, they must run inside a special type of refrigerator called a dilution refrigerator. And you know, when you make these things that cold, obviously it presents additional challenges. All that stuff that you saw in the kind of first picture of our lab is all the infrastructure needed to keep the chip cold. And the chip itself is tiny, about the size of a fingernail. But then you end up with these giant sort of refrigerators and all this extra instruments just to keep that little thing cold. So assuming that you've got your pulse program correct and everything's hooked up and the device is cold enough, you can send it the pulse program and it will physically realize the program on the qubits. Rigetti computing in particular emphasizes a special type of quantum programming called hybrid quantum classical programming. So that's where you can sort of do two things. You can perform qubit operations, but then you can also perform classical operations like if statements and so forth in order to kind of modify your program on the fly. Now, unfortunately for software engineers, you don't really have a lot of time to insert any changes into a quantum program as it's happening. So, again, back in my old job, we were pretty impressed if a page loaded within 20 milliseconds. But at Rigetti, the qubit decoherence times means that you have far less than that to insert any classical instructions into the program. So if you want to do some pre-processing in the middle, you really don't even have time to get back to a CPU. And you have to start looking at specialized hardware, FPGAs, and so forth that's also physically close to the device, because even the travel time to get the information out of the computer and back in is going to be in effect when your budget is like 100 microseconds. All right, so we're almost kind of through the cycle of what happens behind the scenes when you run a quantum program. So the final step is obviously to get, as someone who's just submitted a quantum program, is you want the results back. And we call this step readout. So the analog problem is going to show up again here. And that the data coming out of the computer, unlike in a classical computer, is not going to be clear-cut between 0 and 1. There is some inherent inaccuracy in our instruments. There is a bunch of noise in the environment, of course. And so the data that we get out actually doesn't look like straight zeros and ones. It looks more like this. And then we need to do some little bit of classification on this data to realize that, for instance, the orange is the 0 state and the green is the 1 state. But other times it's less clear-cut than this. And there's some ambiguity in terms of readout accuracy as to how certain you can be that a 0 is actually a 0 and a 1 is actually a 1. But anyways, assuming you end up with a nice chart like this where the classification is easily separable, you can return the zeros and ones back to the user. All right, so that's it. That's the full cycle of what goes on behind the scenes at our office in terms of software when you write a quantum program and send it to us. And hopefully that gave you some indication of the kind of software challenges, at least, that we face in order to make quantum computing a reality. Of course, software challenges are just one small fraction of the total challenges required to build something like this, but hopefully, I've kind of scratched the surface of some of the software things. So let's assume you'd like to give this a try, run some quantum programs for yourself against our computers and have them flow through that entire cycle. You can do that. Our website, if you go to it, we've just redesigned our website, so let us know what you think. You can go get an API key, and that'll allow you to execute quantum programs against our simulator. And it's very easy to get up and running. Here's some Python code. To get through that entire cycle of everything I showed you, compilation, pulse program, physically realizing the program, and then readout, that entire thing only takes about 10 lines of code. So here's the Python that you'd need in order to do a Bell state, a couple imports, specify your program using Quill, send it to us using the QPU connection or QVM connection, which is our simulator, and we'll send you back the one piece of data or one bit string for each shot that you've asked for. So in this case, we've asked for a Bell state with 10 shots. We get back 10 pairs of binary numbers representing the readout for those quantum programs that were performed. And if you get tired of the simulator and would like to run on real quantum hardware, we can set that up for you as well. So please feel free to email support@rigetti.com or talk to Ryan here or email him, ryancarl@rigetti.com. We'll get you set up running against some of our physical devices so you can try out how your program responds under realistic noise. So what are people in quantum information using our platform to do? A whole number of things. So some of our users in quantum computers, quantum information, are interested in, for instance, characterizing the quantum computers, reducing the effect of noise, or building more robust layers of interaction to make quantum computing more accessible. Other users are more set on getting the most out of our existing quantum computers by pushing on algorithms that tolerate device noise, or by pushing quantum information along information theory and computer science to try and find new uses for quantum computers. So 11 papers in this year alone have been published using our real quantum hardware, both the 8-qubit and 19-qubit devices. Many of these users were either new to quantum chemistry or quantum information. However, they were able to take advantage of our software tools and community software tools such as OpenFermion to take their ideas, take their research, and physically realize it. So OpenFermion is pretty cool. It's an electric structure package for doing VQE, which is a particularly promising one of these hybrid algorithms. And we've seen a lot of people this year do very meaningful work against our platform. So if you're interested in any of this, which I imagine you are, hopefully, like I said, you can sign up for free right now in a few minutes to access our simulator. If you'd like to access the real quantum hardware, come and talk to Ryan or email him. And of course, if you're interested in specifically the software side, I'd love to talk to you. There's my Twitter and there's my email. So thank you very much for inviting me here to IQC.
Questions for Stephen? Is that me?
Yeah.
Pointing over, Neil.
Yeah, great. Overview, but okay. You talked about the pulse step.
Yeah.
You have 20 microseconds to kind of communicate. Can you zoom in and kind of talk us through some of the design choices there? Like, how do you actually accomplish that?
Yeah, so because you only have, well, you have whatever the coherence time is, which is getting better than 20 microseconds lately, but you really don't want to put a classical computer in any step of that. So we send the entire program to some pulse generators, control hardware, and then we synchronize the time across all of these different pulse generators. So there's one per qubit. And we'll synchronize the time across all these instruments and then give it an exact start time down to the nanosecond, basically. And then the instrument itself is able to just play the entire program in real time and be synchronized with all the other instruments. So you basically, I guess the short answer to your question is you're giving the entire pulse program at the beginning. It's not something like where you're going through a loop and then saying, pulse.run, pulse.run. You need to package up the whole thing at the beginning, send it out, synchronize the time, and then trigger the execution. Otherwise, there's literally no hope of getting any kind of classical feedback within that time. Other questions?
So, people are imagining what it's going to look like, what is the stack going to look like when you incorporate quantum error correction, which has this measurement and feedback, and usually you have a decoder in mind, and sometimes it's a non-trivial kind of decoder. So we imagine because it has to be very quick, we'll use either an FPGA or application-specific chip. But for the NISQ era or the near-term era of variational algorithms, maybe using like an FPGA, you hinted towards it, but like using an FPGA that could run your optimizer maybe all in the fridge or something, that would be like really fast, right? So
yeah.
If you cut like 3 orders of magnitude on your time between your classical optimizer and your next program, then that would really increase the wall clock time of running some of these algorithms, which can take some time because there's a lot of samples for now, right? Like finite difference gradient and all these things. So is that something?
Yeah, I think.
I don't want you to spill the beans here.
I think the direction that we're going is that first we'll start out with being able to kind of program in very specialized use cases such as error correction, such as fast reset. Fast reset is where once you read out a qubit, if you see that it's in the 1 state, you immediately apply an X pulse, and that will allow it to relax to the 0 state faster than just waiting. And that would allow you to take, your shot rate would be much higher. So specialized uses like error correction, rep rate, fast reset rather, I imagine we'll see sort of custom designed hardware put in the fridge or beside the fridge to run those things. But then the direction that we want to go is general purpose classical programming, where we make no assumptions in the hardware about exactly what the classical feedback is going to be. And so Quill supports this at the language level, which it has, it's Turing complete. It has full set of classical instructions in architecture as well. But the hardware is going to need to catch up to be able to perform kind of arbitrary classical interventions during the program. So these sorts of specialized uses I can see coming pretty soon, but in order to support the more general classical case, the language supports it, but the hardware will need to catch up.
Question?
Yeah.
So the classification task and readout, how different is that between different machines, and how often do you have to calibrate the readout?
Very different and really often. So each individual qubit is going to have kind of its own personality, I guess, and each one of them also varies in our accuracy and our ability to accurately determine whether something is a 0 or a 1. So the one that I showed you in the slide was a particularly nice case. We can measure the readout fidelity by saying, basically what's the likelihood that if you think something is a 0, that it was truly a 0. And you can get figures up in the high 90s. Other qubits are not going to look that nice. You'll see those two kind of big blobs of points overlap a little bit. And then if you end up with a point that's in the middle, you really don't know whether it's a 0 or 1.
Hillary?
I mean, as for the control system, if you have to worry about distance separation, obviously the obvious thing to do is to put the control software inside the fridge. But the trouble with that is an off-the-shelf field programmable gateway. You stick that in the fridge, it's going to stop working because you're below the threshold temperature for the semiconductor.
Yeah.
Are you looking at specialist hardware? You don't need that big complicated a circuit. What you need is for it to be able to tolerate extreme low temperatures. Are you looking at that? Because NASA has this problem. This is what their space probes keep dying off on Mars, right? If they get too cold, the circuits pack up. That's why space probes have heaters to keep the circuit.
Yep.
So they stop working if they get too cold. And those temperatures happen on Mars, which is tropical. Your device. So are you looking at that? And have you compared notes with NASA, who are presumably looking at this problem as well?
Yeah, so I think the trend is that these kind of generic off-the-shelf components that we have been using for generating the pulses and doing readout are not going to work in the long term for a number of reasons. Another reason is just that sometimes they're too accurate or sometimes they're not accurate enough. So with quantum computing and with our pulse programs, we care about very specific things that the original hardware manufacturers of these kind of generic devices may not have cared so much about. And one of those would be, for instance, the ability to run under low temperatures. So I think really the only solution at that point is to start looking at some more customizable parts.
So during compilation, you've been doing a bunch of swap gates, different qubits that are non-local on the hardware together, and then to qubit and then back to where they started, right?
Yeah.
How does the fidelity of the swap gates impact how interconnected your quantum algorithm can be with unitaries and 2 qubits and 1 qubit states all over the place?
Yeah, so it has a major effect, obviously. Any additional 2 qubit gate you add to the program is going to decrease the overall program fidelity by some measure of the individual 2 qubit gate fidelity. And at this point, adding a handful of these to your program is not going to be a good thing. So we're not at the era of kind of generalized quantum programming yet. People need to ideally be aware of the connectivity of their device, of our devices that we have on offer, and try and sort of program around that. as opposed to being hardware agnostic or unaware of the device and relying entirely on the compiler to give you a program that would be high fidelity.
What is the fidelity swap rate?
You can find all the fidelities of all our devices actually on our website. So we have an 8-qubit device, which is the current live one, and we will periodically, about once a week, update the fidelities. We update the readout fidelity, the 1-qubit gate fidelity, 2-qubit gate fidelity, and the coherence times. And that's all public. You can find that on our website.
Okay, let's move
Cool.
on to our second talk, and thanks, Stephen, again.